So this question here looks at the properties of functions, specifically stationary points when it comes to the graphs of the function. Now, a property I want you to remember with stationary points is they're also called turning points. So what that implies is it's the point where the curve does a turn and actually comes back on itself. Whether it goes up, turns and comes back down, or goes down, turns and comes back up. Now they're called stationary points because if we imagine these curves represent, for example, a bouncy ball which we throw up into the air or we bounce down on the ground, at some point that bouncy ball will have to turn back on itself. Whether it hits the ground and bounces back up, or whether it reaches its peak and comes back down under the force of gravity. At that point where it turns round, regardless of whether it's hitting the floor or just up in the air by nature, for a micro nanosecond, as it turns round, it is stationary, i.e. the speed of it is equal to 0. Now we know if we've got a function f of x, the speed is represented by the derivative, f dashed of x. Now in order to represent that stopping for that microsecond, what I'm going to do is set f dashed of x equal to 0, solve it and I'll get the x coordinates of the stationary points. What I'll then do is take each of those x points and substitute them into f of x to get the corresponding y values of the coordinates, and I can then use a nature table to determine if they're maximum or minimum, i.e. going up and coming back down, or going down and coming back up. So let's break this down, do it step by step, and see how we get on. First thing I want to do is calculate f dashed of x. So if I take the function, remember for derivatives, bring the power down, reduce the power by 1. What I'll end up getting is 3x squared plus 6x minus 9. And what I'll do is I'll set it equal to 0. Then we solve it. It's a quadratic. To solve a quadratic, we factorise. So I'll end up getting 3 bracket x plus 3 x minus 1 equal to 0. So I'll use a common factor first, then my trinomial technique. Once I've done that, I'll be able to get two solutions from it. X is equal to negative 3 or x is equal to 1. So those are the x values of the stationary points of the curve. Now in order to get the y coordinates, I'm going to substitute each of these into f of x and it will give me the corresponding y value for that x value. So if I do f of 1 first, what I'll end up getting is 1 cubed plus 3 times 1 squared minus 9 times 1 plus 5. And if I work all of that through, I'll get a value of 0. So that then means I've got one stationary point at 1, 0. Now if I do the same for x equal to negative 3, I'll get f of negative 3. So I'll end up getting negative 3 cubed plus 3 times negative 3 squared. Take away 9 times negative 3 plus 5. And if I work that all through and calculate it, I'll end up getting a value of 32. So that means my second stationary point is at a value negative 3, 32. Now you can kind of get an idea from this of how the shape's going to look. We'd anticipate with the heights of these two stationary points as we move along that the curve would look something like that. That's what we'd anticipate. However, we have to prove it, and we're going to prove it using a nature table. Now to set up a nature table, we need 3 rows. The first row is going to represent x, the values of x as we move along the axis. The second one is going to represent our f dashed of x. Now it's not going to be worrying about too much about calculating the values of the derivative. What we're going to look at is the sign of the derivative. How does the behaviour look as we move along the x-axis? And then I'm going to set up our last row, which we're going to call graph, and that's just going to represent the graphical look of it, i.e. we can show whether it's going up or down at each of those points. So what we'll do is we'll set up the first chunk here. It's going to represent the value of negative 3. So I'm going to have a negative 3 there. I'm going to look at a value below negative 3, and I'm going to look at a value above negative 3 to represent the typical behaviour. Now I'm going to leave a gap. This here is just all the things that happen between negative 3 and the other turning point. And I'm going to set it up. Same idea. There's my second stationary point at 1. And I'm going to look at what the values below 1 look like and what the values above 1 look like. Now I know my derivative at -3 is 0, same with 1, so that means my graph for both of those is going to be nice and flat. If I look at any value below -3, and I imagine taking that, now the bracket with x minus 1 is always going to be negative. At this point below -3, that's a given. If I look at the second bracket, the x plus 3, if I have a number whose magnitude is bigger than 3, but whose sign is negative, and I add 3 onto it, I'm going to get a negative value every single time, no matter what. If you don't, you've done maths wrong. So what that means is ultimately any time below -3, my two brackets are going to give me a negative times a negative. If I do a negative times a negative, it's going to give me a positive value. So below -3, my derivative is going to be positive. That means my graph is coming up. It's got a positive gradient. If I look at a value above -3, let's say, for example, -2, my x minus 1 bracket is going to be negative, but my x plus 3 bracket is going to be positive because the size of the number is going to be smaller than 3. So even though it's negative, if I add 3 onto it, it's always going to push it into a positive value. So I'm going to have a positive times a negative, which means at this point, above -3, my derivative is going to be negative, so it's going to come down. Now nothing else happens between -3 and 1. There's no other changes, there's no other stationary points, nothing like that. So what I can do is actually say that means then below 1, I know it's going to follow the same pattern as above -3, so it's going to be negative, so my curve is coming down. At 1 it's 0, and then if I look at any value above 1, the x plus 3 is always going to be positive no matter what. And if the magnitude of my number is bigger than 1, and I take away 1 from it, that's going to be positive. Positive times a positive, that's going to give me a positive value overall, so it's going to come back up. So what I can then do is say, fine, I've got two turning points, two stationary points. At 1, 0, it goes down and then back up. So that's what we call a minimum turning point. And at the second value, -3, 32, it goes up, then comes down. So that there is our maximum turning point. So we've answered all parts of the question here at this one. Now a question like this is actually typically worth quite a few marks. It's worth about 6 marks, this one. You get 1 mark for starting to differentiate. Any of the terms here, any single term will get you a mark. You're showing you know the technique for differentiation. Completing the differentiation and setting it equal to 0 will get you a second mark, showing that you know the technique, but you then also know the theory behind it, i.e. f dash of x has to equal 0. You get a third mark for getting both values of x. You'll get a fourth mark for determining the two values of y and having your two coordinates. Your fifth mark comes through here from the stationary point, working it out in terms of its nature, using the nature table. And then your sixth and final mark, one of the key things that we have to work on, is our communication, i.e. what's your conclusion to it. So tell me, what are the two turning points, what are your two stationary points, and what type are they? Are they minimum, are they maximum, or could they even be a point of inflection? Now we don't have an example of that here, but that is another scenario which could come into play. So there you go, working this question through. If we follow those steps and look at that idea behind it all, and make sure we don't miss out any of these bits of information, we should manage to score full marks in a question like this, and we should manage to nail it. Easy peasy, lemon squeezy.